In this video, I'll show you how to monitor Golang app using Prometheus. We'll use all possible Prometheus metric types. For the first graph, we'll use a gauge to keep track of all connected devices to the app. It's also very common to expose some metadata about the app using Prometheus metrics as well. For example, you can expose currently running version of the app. Then the counter, its value can go only up. We'll use it to count the number of upgraded devices. By itself, counters are not very useful. That's why they usually used with other Prometheus functions, such as rate. In this example, we'll count the number of upgrades performed by our app per second. Next is histogram, which is typically used to measure request duration and response sizes. We'll use it to calculate the latency for the requests. By using PromQL built-in function, we'll calculate the P99 percentile. That means that 99% of requests will be faster than the given latency number. Also P90 and P50, which is actually just a median. Finally, we'll use the summary metric type to calculate similar percentiles. Also, we'll discuss the differences and I'll share my opinion on which of them you should use and why. We'll build the app from scratch and use Docker to run it. To simplify setup, we'll create a Docker Compose file and run the Golang app, Prometheus and Grafana using Docker Compose. First of all, let's create a folder for the Golang app. If you're on Linux or Mac, you can run the following command. Then we need to switch to the My App directory. Start your module by using go mod init. Replace the path to your source code repository. Now let's create the bare minimum application to expose default Golang metrics via localhost 8081 metrics endpoint. For this tutorial, we're going to use a standard HTTP module to create HTTP API to manage hardware devices. Run go mod tidy to download the Golang Prometheus client. To start the app, you can run go run main.go. To get default metrics exposed by the Go app, you can use curl. Most of the time, these metrics are not very useful. It's a good practice only to expose and collect metrics that you actually need, especially if you use one of many managed Prometheuses that charge by the number of metrics and storage. Moving forward, we'll disable default metrics. We'll start with a gauge metric type. It represents a single numerical value that can arbitrarily go up and down. For example, you can use it to measure current memory usage or the number of concurrent requests. We'll use it to keep track of the number of connected hardware devices to our app. Also, the typical use case for the gauge metric is to expose some metadata about the app. For example, the app version using the label. Let's go ahead and create a struct to represent the hardware device. It's going to have ID, MAC address, and firmware version. Then declare the slice of the devices as a global variable to hold all the connected devices. Use the special init function to create a couple of devices. The init function will run before the main and is used when you need to set up some form of state on initial startup of your program. Now let's create HTTP handler function that returns all the connected devices to this instance. Use json.marshal function to convert Go structs to the JSON string. Check for the error and return the bad request status code in case of the conversion error. Then set the content type header to application/JSON and use the 200 HTTP status code. Finally, write the data to the connection. In the main function, add a new devices endpoint and use getDevicesHandler function that we just created. Use curl to check if you can return connected devices. You should get 2 devices. It's time to declare our first metric. We're going to use a gauge to maintain a number of connected devices to this app. Create metric struct and set devices property to the Prometheus.gauge type. You may notice that you can use either gauge or gauge vector. The difference is very simple. Gauge represents a single numerical value, when gauge vector is a collection that bundles a set of gauges with the same name but different labels. For example, if you want to count all the connected devices and you don't care about the different types, use a gauge. On the other hand, if you have different device types, such as routers, switches, and access points, and you want to count them separately, use gauge vector with a type label. You'll see a bunch of examples during this tutorial. Then create new metrics function that defines metrics. It accepts Prometheus register and returns the pointer to the metrics struct. We need to create devices metric using the new gauge function. A namespace is just a metric prefix. Usually you use a single word that matches the name of your app. In my case, it's my app, then the metric name. It's important to follow the naming conventions provided by Prometheus. You can find it on the official website. Let's call it connected devices. You also need to include a metric description, then register it with Prometheus registry and return a pointer. In the main function, create a non-global registry without any pre-registered collectors. Then create metrics using the new metrics function. Now we can use devices property of the metric struct and set it to the current number of connected devices. For that, we simply set it to the number of items in the devices slice. Let's also create a custom Prometheus handler with a newly created register. We also need to update metrics handler to prom handler. If you try to scrape the metrics endpoint right now, you should get a single connected devices metric with a value of 2. Optionally, if you want to keep all the Golang default metrics, you can use built-in collector to register it with the custom Prometheus register. Also, you can expose Prometheus handler metric as well by adding registry field. The next info metric will represent the metadata about the app. You can expose any number of arbitrary key value pairs from your application. As an example, we'll expose the version of the currently running app. This time, this will be gauge vector type, since we need to set a version label with the actual version of the application. Let's declare info metric using new gauge vector function. All the metrics will get the same namespace with the name of the app. Using the same naming convention, let's call it info as well and give it a description. Don't forget to register it using must register function. Then declare a global version variable. Typically, this variable will be set using environment variables or by your CI tool. For the demo, let's just hardcode it in the init function. Then in the main function, we can use the version Prometheus label to set the application version and use a constant value of 1. If you check default Golang info metric, it uses the same convention. If you check the metrics endpoint, you should get the info metric with the version of your app. I'll show you later how to use it in Grafana. It's more common that you may think to expose Prometheus metrics endpoint using a different port. It helps to keep it secure and private by configuring firewall rules and access lists. For example, in AWS, if you deploy your application using EC2 instances and Elastic Load Balancer, you can easily expose your main port/endpoint to the internet and keep your Prometheus metrics endpoint private and protected. Since we don't use any third-party routers or frameworks, I'll show you a very simple way to run multiple servers using Go routines. The key is to create separate HTTP request multiplexers. The first one is default multiplexer. We'll use it to serve the main content. Replace HTTP with your custom multiplexer. Then the second one is for Prometheus. Spin up the first Go routine for the main server and the second one for the Prometheus metrics endpoint. Then to prevent main function from exiting, we can use a select statement that blocks until our Go routines are running. Now, if you access localhost 8080/devices, you get connected devices. But to get metrics, you would use localhost 8081/metrics endpoint. The next step is to set up Prometheus and Grafana locally using Docker and Docker Compose. It's optional, but can help you to visualize your metrics. Let's create a Docker file. I'm not going to spend a lot of time on it. In the first stage, we want to import files and build Golang binary. In the second stage, we take a distroless image and copy our binary there. For the local development, you can just use a single stage and perhaps find a way to reload and rebuild the image automatically on any change. To run it locally, we'll use a Docker Compose. In that file, define my app service and specify the path to the application. Docker Compose will automatically build the image when we run app command. We also want to expose ports 8080 and 8081 with the Prometheus metrics. By the way, the service name, in this case my app, also becomes the fully qualified domain name that can be used by other services in this Docker Compose file. For example, Prometheus will use it to find its targets. To start the app, run Docker Compose app. We also need to add for the future run build argument. When we make any changes to the source code, we need to rebuild the Docker image. Now test with curl if you can access localhost 8080/devices and localhost 8081/metrics endpoint. The next step is to run Prometheus. Create a folder Prometheus and corresponding configuration file. For the scrape interval, you can use such small values, but in production, you want to increase them to at least 15 or 30 seconds. We're not going to specify the alert manager and any rules. We'll use static scrape config with the domain name of my app. If you don't use Docker Compose and run it locally, just specify localhost 8081. We don't need to provide the metrics path because it's default. In case you use any different path such as Prometheus, you'll need to specify it as well. Now, in the Docker Compose, add the Prometheus service with the latest Docker image. Expose Prometheus 9090 port to localhost. Finally, provide the path to the local configuration file. Let's run Docker Compose. You can omit the build flag if you want. If you navigate to localhost 9090, you should see Prometheus UI. Under the target section, you can find a single My App target. From the Prometheus Explorer tab, you can enter My App Connected Devices metric and execute. You should get 2 connected devices. There is also a Graph tab to visualize metrics, but most of the time I use Grafana for that purpose. Next is Grafana. We can add a new data source using code. Let's call it main and use Prometheus 9090 URL. Then add the Grafana service to the Docker Compose file. Expose port 3000 to the local host. Set the admin user and password using environment variables. Mount the data source file that we just created to the Grafana container. If you want to persist data such as dashboards between restarts, you must create a volume and mount it to the container as well. Let's run Docker Compose app again and visit Grafana on localhost 3000. The username is admin and the password is DevOps123. First of all, make sure that the data source is properly configured. Then create a new dashboard and let's call it My App. Add a new panel. For the title, let's use Connected Devices Gauge. Make sure that the main Prometheus data source is selected. Use the same metric My App Connected Devices to get all the connected devices to our app. For the legend, we can use instance label, which is automatically assigned by the Prometheus. Change the time interval to last 1 hour. Now let's start customizing our chart. Let's shift the legend to the right and transform it into the table. Choose the last non-null value. Change the line interpolation to smooth. Increase the line width to 2 and set the fill opacity to 50. Also, change the gradient mode from none to opacity. Optionally, you can connect null values. For the unit, use short. Set decimals to 0. Lastly, let's change the color scheme to light blue or any other color you want. That's all. This is our first graph. Next, let's create another panel to display the current version of the app. Change the title to App Version Gauge. Also, update the chart type to stat. For the metric, use myAppInfo. Change the query type from range to instant. For the legend, let's use version label. Set text mode to name and graph mode to none. It's not perfect. Every time you upgrade your app, you'll see multiple versions for 5 minutes. After that, the single version is displayed. Let's add functionality to our app to register new devices. Create a new create device function with the same signature as any other HTTP handler. Then declare device variable. This function will accept device as a JSON object from the client and decode it to the Golang struct. Since we use a global variable to maintain connected devices, let's append this device to the DVS slice. Set the HTTP status code to 201 and return device created to the client. The standard HTTP request multiplexer doesn't have functionality to route requests based on HTTP methods such as get, post, etc. To implement this, we need to create another handler and use a switch statement. Let's call it register devices. Use the switch on the request method. If the method is get, we want to use our first get devices function. If the method is post, use the new create device function. In case we receive a request with unsupported method, we want to indicate what methods are available and send the error to the client. Then update getDevices HTTP handler to register devices. This time, when you run Docker Compose, make sure to include the build flag, since we updated the source code. To create a new device, use curl and provide the JSON object. To check if the device was created, use the get request. Now, every time when we create a new device, we want to increment the corresponding metric. In this tutorial, I'll show you a few methods from creating our custom HTTP handlers to the middleware. Let's start with a custom handler. In order to confirm to the handler interface, we need to implement a single server HTTP function with the same signature as HTTP handler. That's the only requirement. First of all, let's create register device handler struct and include a metrics property that we can pass later to increment the device count. We can update existing register devices function to server HTTP. Then add metrics as additional argument to the create device function. In the create device function, add metrics as a third argument. To increment device count, you can use inc method. In general, it's recommended to use set instead with gauge type metrics due to performance benefits. On the other hand, it's better to use increment on the counter type than set. Let's use the latter. In the main function, we need to initialize register device handler and pass a pointer to the metrics struct. Then replace the handler on the device's endpoint. To test this functionality, rebuild the app. You can use the same command to create a new device. In the Grafana dashboard, you can see that the metric went up. The next metric type that we're going to implement is a counter. It is a cumulative metric that represents a single monotonically increasing counter. It can only go up and be reset to 0 on restart. Typically, you would use it with the rate function and measure the number of requests served, task completed, or errors. We're going to use it to count device upgrades. Let's declare it as a counter vector and add custom labels. We'll use a label to count upgrades of different device types. For example, the type can be a router, access point, modem, etc. Add it to the new metrics function. Let's name it device upgrade total and give it a description, number of upgraded devices. Provide a single type label and don't forget to register it using must register function. Next, create upgrade device function that accepts writer, request, and metrics. To get the ID of the device, let's trim the path. Let's try to convert ID to the integer and return error if it fails. To accept firmware version, we'll reuse the same device struct to decode JSON to the device object. Then find the device by the provided ID and update the firmware version. To increment the counter, use a router type label and inc method. Return 202 HTTP status code and send upgrading message to the client. We also need to create a custom HTTP handler with metrics property. For the upgrade of the device, we typically use put HTTP method. On any other request, send method not allowed. In the main function, we need to initialize the new manage devices handler and add additional devices path with a slash at the end. Rebuild the app. Until you upgrade at least once, you won't see a new metric in the Prometheus. Let's use curl to upgrade a device a couple of times. Now, in the Prometheus, you can execute my app device upgrade total query to get the number of times your devices were upgraded. Just a total number of upgrades may be not very useful. More interesting would be to measure the load. We can apply the rate function to get the number of upgrades per second. Let's create a new Grafana chart and call it upgrades counter. Use rate my app device upgrade total query. In this expression, we measure the rate of the upgrades per second for the last 1 minute. Keep in mind that the interval must be at least 4 times larger than the scrape interval. For the legend, let's use type label. Then pretty much the same customizations as with the previous dashboard. For the unit type, use requests per second. Change the color to pink. Set refresh rate to 5 or 10 seconds. Before testing upgrades, let's introduce some artificial delay. Create a new sleep function. It accepts the maximum number of milliseconds and generate some random delay. Then include it in the upgrade device function. Rebuild the app. Now, to generate some load, you can run curl multiple times, or you can use one of the many load testers such as Hey. To measure latency or response sizes, we typically use a histogram. There is a significant benefit over summary that I'll show you in the following example. Let's create a new metric and call it duration of histogram vector type. When naming histograms, you should follow Prometheus naming conventions and use one of the base units. When measuring time, instead of minutes or milliseconds, you should use seconds. Later, you can convert it using either simple math or built-in Grafana type system. The key and sometimes a challenge when working with histograms is that you must come up with some time buckets ahead of time. On the other hand, a summary doesn't require it, but there is even a bigger issue with it. You can use some built-in functions to automatically generate buckets, or you can hardcode them. Here, for example, I want to declare 5 buckets from 100 to 300 milliseconds. They used to count requests. For example, if the request duration is less than 150 milliseconds, the bucket count will go up. Let's use one of the custom handlers to pass the metrics variable to the getDevices function. Add metrics as argument to getDevices. Then get the current time. Use sleep to simulate some latency. Finally, record the observation using observe function and the time elapsed since now. Later, I'll show you how to measure duration by creating a custom middleware. Rebuild the app. Until you at least once invoke /devices endpoint, the new histogram metric won't show up. Before creating a dashboard, let's scrape the metrics endpoint with curl. We have all the buckets with the upper inclusive bound, including the sum and count. Duration seconds sum is the total sum of all observed values. Since I invoked devices endpoint just once, it looks like the duration of that first request was around 65 milliseconds. Duration seconds count is the count of events that have been observed. Since I made a single request, we have a single count. Now let's create a new Grafana chart for the request duration. Let's call it latency histogram. For the query, let's calculate multiple percentiles and start with P99, which covers 99% of all requests that fall under that duration. Here is the biggest difference, in my opinion, between histograms and summaries. You can easily aggregate histogram values across all the replicas of your service. Especially in the cloud, we usually run multiple replicas of the application, sometimes even hundreds of them. When using a summary, you can only calculate the percentile for each individual application. On the other hand, with histogram, it's easy to aggregate across all the replicas. Also, histograms cover almost or maybe even all use cases for summaries. As I said, the downside is that you need to set up buckets ahead of time. Even if we have a single application right now, let's make this query future-proof and update it. For the legend, use P99. Let's also repeat the same process for P90 and P50. Then make the same customizations for the graph. For the unit, use seconds. Optionally, you can override some variables. Change the color for P99 to red. Then for P90, use yellow. Finally, for P50, you can use green color. Now let's generate some load. The last metric type is summary. It's a little bit more convenient than a histogram in a way that you don't need to define buckets ahead of time. But it's not possible to aggregate across multiple replicas of your application. I almost never use it. As with any other metric, you can declare it as a summary vector. But for simplicity, let's just use a summary. Let's call it login request duration seconds. When you declare the summary vector, you can specify percentiles instead of buckets. Here we have the same P99, P90 and P50 percentile. Also, don't forget to register it using must register function. For the summary, let's create a new login endpoint and a handler, but in this case we'll use a middleware pattern. First, let's create a similar custom HTTP handler, but without the metrics property. The handler will only use the sleep function and return welcome to the app to the client. Now the middleware. It accepts the HTTP handler and the metrics and returns another HTTP handler. In this way, you can chain as many middleware functions as you want. For this use case, we only want to measure the duration of the request. Let's record time now and then a similar observe function right after the HTTP handler. In the main function, declare login handler, then use middleware to wrap it. Finally, we can use it in the login endpoint as a handler. Rebuild the app. Let's try to access login endpoint. If you scrape metrics endpoint again, you'll see similar output as the histogram. But instead of buckets, you have the percentiles that were computed on the server side already. Let's create the last graph for this tutorial. Call it latency summary. For the query, use myapp login request duration seconds quantile 0.99 metric with different values. The first is P99. Then P90 and P50. For the unit type, use seconds as well. Also, if you want, you can override some variables to match the histogram graph. For the final test, let's generate some load. Thank you for watching, and I'll see you in the next video.